All right, open your book up to section 10-6. Again, we're on page 539 in your book. The title of this section, again, is the Parametric and Cartesian Equations for Rotated Conics. The objective is to plot a conic section rotated by a specified angle to the coordinate axes. The second part of the objective is identify a rotated conic from its Cartesian equation. And the third part here is to plot a rotated conic using its Cartesian equation or parametric equation. Now, we've already tackled the parametric equations in the first half of this section. And you'll recall that we use that rotation matrix in order to do that. Take the rotation matrix, multiply by the parametric equation, add on our translation that we need, and we end up with a rotated conic. For the Cartesian equation, which is what we're going to tackle here in the second half, you've seen that written in a couple of different forms here. We've had that center radius form for the ellipse, the circle, and the hyperbola. And we had that vertex form for the parabola. And then you also saw that all three of those, or all four of those, we can write in the polynomial form. That's that ax squared plus bxy plus cy squared and so forth. In fact, all the problems we've dealt with up to this point, we've said we're going to let the xy term be 0. We're going to let the b equal 0 in that equation. And we'll see here today that when we allow that value to be something other than 0, that's when we end up with a rotation. All right. Let's take a look at an example here then. Turn to example 2 here in your book on page 542. This example says, plot the graph of the equation 9x squared minus 40xy plus 25y squared minus 8x plus 2y minus 28 equals 0. Let's go ahead and write down that equation. So we've got 9x squared minus 40xy plus 25y squared minus 8x plus 2y minus the 28, that's equal to 0. Now again, if we just look at this and use the same analysis that we've previously used to figure out what kind of conic we have here, we'd look at the x squared term and we'd look at the y squared term and we'd say, well, those are both positive, but they're different values. So therefore, based on our previous analysis, we'd say that this is probably going to be an ellipse. Okay, now we've already talked about the fact that we're adding an xy term in here, and we're just going to check to see if that changes anything here for us. But let's go ahead and plot this and see what happens. Grab your calculator and let's try this out. You have a program on your calculator that will plot conics for us. So go to your program and go to Conic. And we'll punch in the equation that they gave us here. Again, it was 9x squared. It was a negative 40xy, 25y squared, a negative 8x, positive 2y, and a negative 28 is what we'd have there. And there we go. Here's our sketch of this thing, and I think we can clearly see that, well, we don't have an ellipse here. This looks like it's a hyperbola, actually, is what it looks like we end up with. In fact, let's grab a picture of that. And we'll paste it into our sketch here. So our initial idea here that I can just simply look at the x squared and the y squared term to determine the conic, that works as long as b was equal to 0. But as soon as b is no longer equal to 0, I can see that's no longer the case. This is not an ellipse. This is a hyperbola. And what we should notice here then from this is that it is true that a and c determine the conic, but b must also be playing a role in determining the conic. This part right here, the xy term, must play a role in this. All right. Let's take a look at the next example. Look at example 3 there on 542. It says plot the graph of the equation 9x squared minus 20xy plus 25y squared minus 8x plus 2y minus 28 equals 0. Well, that's the exact same equation, but they've changed the coefficient of the xy term there. They've changed the value of b. So we've got 9x squared minus 20xy plus 25y squared minus 8x plus the 2y minus the 28 equals 0. Now again, we already know that I can't just look at the x squared and the y squared term to determine the conic, because these are the exact same numbers I just saw a second ago. So my prediction here would be that this would be an ellipse, but again, I know b must be playing a role in this. So let's go ahead and check out what kind of conic this is. Grab your calculator again, and let's graph this instead. Now the nice thing about the program that you're running there is it's actually storing the values of a, b, c, d, e, and f for me. So actually I don't have to rerun the whole program. I can just simply take negative 20 and store that as the value of b. And remember, over in your y equals menu, it's got this big long equation here in terms of those 6 values there. So I can graph this now, and I don't have to run the program again. Oh, that turns out to be an ellipse. Turns out this one is the ellipse. Again, let's grab a picture of that. So this does in fact turn out to be an ellipse. Okay. All right, let's take a look at one more example. If you look at example 4 there on page 542, it says to plot the graph of the equation 9x squared minus 30xy plus 25y squared minus 8x plus 2y minus 28 equals 0 on the same screen. Okay, so they again have given us the exact same equation, but they've changed the value of b. And so now it's a 9x squared minus 30xy. Well, you probably can predict already based on the previous two graphs that we saw there what this is going to end up being, but let's see what we end up with. So plus 25y squared minus the 8x plus the 2y minus 28 is equal to 0. All right, let's go ahead and punch that into our calculator and see what we end up with. Again, the cool thing about that program you got there is I can just change the value of b to negative 30 this time. And when I graph that, it will regraph it for me. And you might have to zoom out a little bit to kind of verify for yourself that this is not a, it's hard to tell. Is this an ellipse that's just, I'm looking at just part of it? Could this be a hyperbola? And there's another section over here to the left that I don't see. But if you zoom out far enough, you'll convince yourself here that this, in fact, is the parabola, is what we're looking at here. So let's grab a picture of that. All right, and we'll just make a note here that this is the parabola. All right, so the method that we've seen up to this point to determine the type of conic when it's in this polynomial form for the Cartesian equation, where we only looked at the x squared and the y squared term, that is, we looked at the a and the c value, that will work as long as b was 0. But now all of a sudden when I change b from being a value of 0 to something else, now the conic is changing here. So I know that a, b, and c play a role in determining the conic. So what is the role that it plays? Well, it turns out that's called the discriminant of your conic section. So given a conic equation here, or the equation of a conic in Cartesian form, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, it turns out you can determine the conic based on the relationship of a, b, and c. So here we go. It turns out that you're going to end up with a circle if b squared minus 4ac is less than 0. And a and c have to be equal to each other, and b also has to be 0. That's the only way that you're going to end up with a circle. A and c have to be equal to each other, and b has to be equal to 0, which is actually the same way we defined what a circle was earlier in this chapter. Turns out you end up with an ellipse if b squared minus 4ac is less than 0, but a and c are not equal, and b is and not 0 there. It turns out it's a parabola if b squared minus 4ac is equal to 0. And it turns out it's a hyperbola if b squared minus 4ac is greater than 0. Now, if you notice there, I put this in I carefully have arranged this in this order here. This is the same order when we looked at the eccentricity of our four conics, that in increasing order, this is how our conics lay here. If your eccentricity is 0, you got a circle. When the eccentricity was between 0 and 1, it was the ellipse. And then if it was equal to 1, it was the parabola. And finally, greater than 1 was the hyperbola. The nice thing about arranging these in the same order, maybe that helps you remember them and how you come up with the conic based on those four values there. Now, why is that the case? Well, I'm not going to really totally prove this, even though this says proof. It's not really a proof of it, but I'll show you the essence of why this is the case here, that b squared minus 4ac is the special number that we need. I know that I need something that involves a, b, and c. And I don't have to worry about the d, e, and f. You could verify that by playing around with these other equations and changing the values of d, e, and f, and you'd see that the conic stays the same in terms of what kind of conic it is. What we're going to do is we're going to go back to the quadratic equation in terms of y that we used to come up with that program that we just ran there, that conic program, where it just dumps two big long equations in y1 and y2. Let's go back and look at how we came up with that equation. Well, we just rewrote this as a quadratic in terms of y. So let's grab the cy squared term and put him first. And then let's take our two y terms. There's a bxy and an ey. So I'm going to go ahead and factor out the y there. So it's bx plus e times y. And then add that to everything else that doesn't have a y in it. So there's an ax squared. There's a dx. And then there's an f. That's equal to 0. So just reassociating some terms there and doing a little bit of factoring, I guess, to get this quadratic form. This is a quadratic equation in terms of y. We then took this and said, well, we know how to solve quadratic equations. That's exactly what our quadratic formula does for us. So I can solve this for y using my quadratic formula. We said y is equal to, it's the opposite of the linear term here. So it's the opposite of the bx plus e. I'm being careful how I say that because we have a, b's, and c's in this problem already, and I don't want to confuse us with using those same names like we normally use with the quadratic formula. And then it's plus or minus the square root of the coefficient of the y term. That's the bx plus e squared minus 4 times the coefficient of the y squared term, that's c actually, times the coefficient, or times the constant term there. It's not a coefficient of anything. It's just ax squared plus dx plus f. All of that we're taking the square root of. And this is all divided by 2 times, again, the coefficient of the y squared term here, which is 2 times c. Now, the part we have to look at is actually the part that's underneath that square root. So the part that's underneath that square root, let's take a look at how we could rewrite that. In fact, what we're going to do is we're going to actually square that thing out, and that first term out, and we're going to multiply the second term out and see what we end up with. So we have y is equal to, I'm going to leave this stuff here alone. I'm not going to mess with it. So it's the opposite of bx plus e, and then plus or minus, and it's the square root of this big long thing here. So if I take bx plus e and I square that, I end up with a b squared x squared plus 2bx, or 2be times x. Let me put the e in there first. 2be times x, and then plus an e squared. That's that first term. Now let's distribute the 4c through the parentheses here, actually the minus 4c. So you'd have a minus 4ac x squared. You'd have a minus 4dx. And then you'd have, oops, I have a c in there I need. Let me fix that. It should be a minus 4cdx. And then distributing the minus 4c through to the f, I'll have a minus 4cf. There we go. That is all divided by this 2c. All right, now if you look at what you have underneath that radical, that's actually a quadratic equation underneath that square root. It's just kind of a little bit mixed up there. So let's group terms together here, just like we did with this equation to start with. We group things, though, with looking at the y values. Now let's take a look at these x values of things in this square root. So I've got some x squared terms here. I've got a b squared times x squared, and then I've got a minus 4ac times x squared. And oh, check that out. B squared minus 4ac. Let's keep going, though. I've got a 2bx, and I've got a 4cdx that I'm subtracting. So I'll have 2be, and then minus 4cdx. And then finally, the constants here, I've got, I'll put it in parentheses, an e squared and a minus 4cf. There we go. And again, this is all divided by 2c. Now, in this equation, what we're looking for is something that involves just a, b, and c that would determine the conic for us. We already have determined that that's the key there, is I got to find something that involves a, b, and c. And like I pointed out there as we were doing this, it's the coefficient under this radical here, the coefficient of the x squared term, this guy right here. Of everything that's on in this equation here, that's the only part, the only coefficient that involves just a, b, and c. The other ones are going to involve d, e, or f. And that is the part that determines the conic. It's the coefficient of what's underneath this root. It's the discriminant that we have to look at in order to determine what kind of conic it is. And it turns out if that coefficient is positive, it means one thing. If it's negative, it means something else. And if it's equal to 0, so there is no x squared term, it means it's a different type of conic. All right. Let's try using that to determine a conic now. Look at this last example here, example 5 on page 544. They give us an equation here. Let's go ahead and write this equation down. So it's 2x squared, and then minus 5xy plus 8y squared plus 5x minus 56y plus 120 is equal to 0. All right, so there's our Cartesian equation in polynomial form of some conic, and it says use the discriminant to identify which conic the equation represents and confirm it on your graph here. All right, so let's determine the type of conic by calculating b squared minus 4ac and then determining from there what kind of conic it is, b squared minus 4ac. And I would suggest from this point forward that this is how you always determine your conic. Even when b is 0, always calculate it this way. B squared minus 4ac. B squared, that's going to be a negative 5 squared minus 4 times a, which is 2, times c, which is 8. So what's that end up giving us? 25 minus 4 times 2 is 8, times 8 is 64. And if I take 25 and I subtract 64, what do we end up with? A negative 39. Negative 39. That's the value of b squared minus 4ac. And that is definitely less than 0. That's negative. And we just said earlier that if that quantity is less than 0, then I've got two options here. This could either be the circle or it could be the ellipse. You got to be careful not just saying it's the ellipse. If it's going to be the ellipse, though, that means b has, if it's going to be the circle, that means that b has to be 0, which it's not, and a and c have to equal each other, and they don't. So this has to be the ellipse. So we can determine the conic based on that equation now that we have a b value in there. I'll let you punch that in your calculator and verify that, in fact, that is the ellipse, but that's what we should end up with.